Problem 1022 says, experimental studies of cancer often use strains of animals that have a natural high incidence of tumors. In one experiment, tumor-prone mice were kept in a sterile environment. One group of mice were maintained entirely germ-free, while another group were exposed to the intestinal bacterium E. coli. The accompanying table shows the incidence of liver tumors. And this is what it says. It says germ-free. These are the treatments, or E. coli. And if they were germ-free, total mice, we had 49 and 13 in each group. And then tumors, we had 19 and 8. Okay, it says A is how strong is the evidence that tumor incidence is higher in mice exposed to E. coli. Use a chi-square test against a directional alternative. So here our null hypothesis is that E. coli does not affect tumor incidence. Okay, in other words, P1, this is proportion of mice with tumors. P1 is a proportion of mice with tumors in the germ-free group is equal to the proportion of mice with tumors in the E. coli group. And the alternative is that E. coli increases tumor incidence. In that case, P1 would be less than P2. So P2 is tumor rate in E. coli group, and this P1 is tumor rate or tumor incidence in control group, the test germ-free group. Okay, so our table looks like this right now. So let me make our reform the table so that we have the treatment groups, the populations in columns, and the results in rows. It doesn't really matter, but let me just see. So this will be tumors and no tumors, and the two groups are germ-free, and this is E. coli. Alright, so the total number of mice that were germ-free was 49. Total number of mice that had exposed to E. coli was 13. 8 of them developed tumors, and of this group, 19 developed tumors. And here we have 30, and 13 minus 8 would be 5. Okay, so the total in the row is 27. 27 developed tumors, 35 did not, out of a total of 62 mice. Okay, so our expected numbers, I'm going to put in parentheses here. So I'm going to do 49 times 27 divided by 62. 21.34. Okay, and if I do this to all of the other ones, here I will get 5.66. Here I get 7.34. And here I get 27.66. And once again, our chi-squared statistic is going to be observed minus expected squared over expected. And so we have 19 minus 21.34. 13, 7.34. Okay, so crunching this out, here I get 0.2566. 0.9674. Nine 0.197. I guess 0.1980. And here, .7467. So I'm getting a total of 2.168. Okay, so our chi-squared statistic is 2.168, and I'm looking this up in our chi-squared table with 1 degree of freedom. Degree of freedom is going to be 1. It's always 1 for two-way contingency tables. And so 2.168 is in between 1.64, which corresponds to tail probability of 20%, and 2.71, which corresponds to a tail probability of 10%. Okay, so 2.168 is somewhere in there. So the p-values, because it's a directional alternative, meaning that we're expecting one thing to increase or decrease rather than just say not equal to, that means our p-values will be half of our tail probability. So the p-value is going to be between 10% and 5%. Okay, if we use alpha is equal to 0.05, then that means we do not reject the null hypothesis. So we do not have evidence to show that E. coli increases the rate of tumors. Okay. Part B says, how would the results of Part A change if the percentages 39 and 62% remained the same? Okay, so the rate of tumors remained the same, but the sample sizes were doubled or tripled. Okay, so if we doubled or tripled it, then as we saw in another problem, the chi-squared statistic would also double or triple in size. And when we increase, when we make the chi-squared statistic bigger, that makes the p-value smaller. So the results in Part A might change because the p-value will shrink if our sample size increases, but all the proportions stay the same. Okay, so Part B is p-values get smaller, and that might lead us, could reject the null hypothesis. Okay, with the smaller p-value, we could reject the null hypothesis. So that's how it would change.